So in this video we're going to talk about collecting gases, namely collecting gases over water. That is the main thing that is done. So when we're trying to collect a gas that is produced by a chemical reaction, we have a few different options for doing that, but by far the easiest way to do it, especially in a general chemistry laboratory, by far the easiest way to do it is to collect that water, collect the gas over water. What that looks like is something like this. Here we have some reaction. Doesn't have to be this reaction, obviously, but some reaction is producing a gas. We force that gas to flow through this tube here, and that tube has its outlet underneath a beaker that has been intentionally filled with water and then turned upside down. So originally this beaker was completely full of water. So it was filled all the way to the top. There was no gas in there to start off with. And as the reaction produces a gas, the gas pushes its way through the tube, and when it bubbles up inside the beaker, it pushes the water out. So it pushes the water down and out of the bottom or top, I guess, since it's upside down, but pushes the water out of the open end of the beaker. And so the gas that's produced then is collected over the water. The tricky thing here is that the gas that's being collected is not just the gas that was produced by the reaction. This is also water, because water does evaporate even at room temperature, even at freezing, even at the freezing point it will still evaporate. And so we will still have some water in the gas phase that is mixed in with the gas that we're trying to collect. And so what we're going to do to try and account for that is we're going to use Dalton's law, and we're going to take into account the fact that really what we're doing here is we're taking a shortcut. We technically could do this the long way and use the ideal gas law and work out exactly what the pressure of the gas is going to be. Instead, what we're going to do is we're going to use a table. And actually this table, I do not believe, well, I know that is not the correct table number for our book, because it would be in chapter 9. But we do have a table of vapor pressures of water at different temperatures. And so we're going to just use this table to work out, given a temperature of water, what would be the partial pressure of water in our mixture. So if, for example, we were collecting a gas and we were collecting it at 20 degrees Celsius, and we were collecting that gas over water, in our mixture, in our gas that we're collecting, there is going to be 17.55 millimeters of mercury of water. There's not a whole lot. It's a relatively small amount, but it is something that you would need to take into account. And so we're going to do that right here in this practice problem. So it says, in order to determine the rate of photosynthesis, the oxygen gas emitted by an aquatic plant is collected over water at a temperature of 293 Kelvin and a total pressure of 755.2 millimeters of mercury. Over a specific time period, a total of 1.02 liters of gas is collected. What mass of oxygen gas in grams is formed? Alright, go ahead and pause the video and try to work this out yourself, and then come back and we'll work it out together. Alright, so once again we're asked to find the mass of a gas. So we know that we're going to have to find N, number of moles, because that's the only way for us to get at mass in a problem like this. So we need to find the number of moles of oxygen that is formed. And to do that, we need to work out what is the pressure of oxygen, what is the volume, and what is the temperature. We already know R. Now most of this stuff, again, is already given to us. The temperature, we are told, is 293. The volume, we are told, is almost exactly 1 liter, 1.02. The only thing we're not given is the pressure. We are given the total pressure, but But remember that total pressure is not the pressure of oxygen. Most of it is. Most of it is oxygen, but it is not all oxygen. We want the pressure of just the oxygen, not the pressure of the oxygen and the water that's mixed in with it. So what we're going to do is, if the total pressure is the pressure of the water plus the pressure of the oxygen, and we know that the total pressure is 755.2 millimeters of mercury, we need to find this pressure of water so we can subtract it out, essentially. And again, how we're going to do that is we're going to use our little table here. So we're told in the practice problem here that we're at 293 Kelvin. In Celsius, that would actually be 20 degrees Celsius. Because remember, the conversion is add 273 to whatever the temperature is in Celsius to get Kelvin. 273 plus 20 gives us 293. So we are at 20 degrees Celsius, which means the partial pressure of our water is 17.55 millimeters of mercury. So to find the pressure of just the O2, we're just going to subtract 17.55 from 755, and that is going to leave us with 737.65. Millimeters of mercury. So we do need to go ahead and convert that into atmospheres. So again, to do that, you're just going to divide by 760. And that is 0.971 atmospheres. All right. So we have our pressure, we have our volume, we have our temperature. We can solve for N. So just like in the last one, N is going to be equal to PV over RT. So my pressure is the 0.971 atmospheres. Volume is 1.02 liters. 0.08206, I guess I'll put the units in this time. Liters, atmospheres per mole K, and then the temperature is 293 K. All right, so our atmospheres cancel, liters cancel, Kelvin cancels, leaving us with 1 over moles, which is just going to be the same as moles. And so if we do the math here, let's see, 0.971 times 1.02 divided by 0.08206 divided by 293, that is 0.0412 moles. But we're not done yet. We have one last thing to do, because it does specifically ask for the mass in grams. And so just like in the last one, we're going to go ahead and convert that to grams. The molar mass of O2 is 32 grams per mole. So we're just going to multiply by 32, and we will have 1.32 grams of oxygen. Alright, way to go, little plant. Made 1.32 grams of oxygen for us to breathe. Alright, that'll be it for this video. In the next video, we're going to talk about doing stoichiometry with gases, which I know is your favorite topic. So I'll see you in the next one.